Okay, let's call this earn problem number 3. It's going to be of a little bit of a different flavor, so we'll see something a bit new this time. But that said, I would still consider an earn, right, which is essentially a box. This time with two types of marbles, so two different colors essentially. Here it's a black and white board, so we'll consider B black marbles and W white marbles. To start, right? And so I drew this out, and the procedure is going to be a little bit different also. So at each step K, what's essentially happening is that you pick a marble uniformly at random, and all choices equally likely, and you put it back again along with an additional marble of the same color, right? So the idea would be is that if I pick, let's say, this marble out, right, I would then add it back along with a marble of the same color, and the picture would look something like this. So I put the original one back and add one more of the same exact color, right, and so on and so forth. And you should notice right away that the main distinction between this and the previous two problems is that the number of marbles here is increasing over time. So what could we potentially be interested in, right? Which quantity, which random variable? So I'm going to propose we just look at WK, which is the number of marbles of one of the colors, the white marbles, right, in the box at time K. And we can try to again do all the same calculations to give you a little bit of a sense of sort of how this would be applied in practice. This has in fact been proposed within the discipline of economics to model sort of market share and market domination between two competitive firms. So a common example that's given is that think of the number of white marbles, say, as the number of Android phones in the United States, and the number of the black ones being, say, the number of iPhones, right? And so you have two competing technologies, and obviously there are more and more purchases every year of these Androids and iPhones, and so maybe you're trying to see, does one of them end up dominating the market, right? Will there be proportionately much more of one phone versus the other, right? So there are definitely interesting examples and interesting papers on this, so you're welcome to explore on your own, but for now let's focus on getting the mathematics right. So as usual, we're going to start developing a little bit of intuition. Let's write down the state space, right, for this random variable here, right, and then, well, in fact, we'll conclude that it's a random variable in a second. So as usual, we start thinking sort of what potentially the situation could be, and we know we start with W, little w, of white marbles in the urn. I'm going to make a distinction between the W and an omega, right? And clearly you can potentially add some, right? You can add one more. If we had picked one, we would have added one more, just like I did in that example. And certainly eventually you can get, two more than there was initially, and you can get three more than there were initially, and so on and so on and so on, right? So essentially it's the natural numbers starting with whatever W was. Let's think about the omega, the sample space. Right here you have, right, as usual, a lot of different choices. So, one simple-minded choice could just be the natural numbers product with the natural numbers. So maybe this natural number tells us how many white marbles, and this one tells us how many black marbles. And in this case, it would be easy to say that, not X, but now WK. Right, so WK of omega would just be omega 1, right, because omega is then a tuple, right, of two natural numbers, omega 1 and omega 2, right, and maybe this one keeps track of the white marbles, this one keeps track of the black marbles, so that would be one example of a sample space. Another one that's a bit more complicated, going back to our kind of examples with patterns of or strings with zeros and ones, we could try 0, 1, n, which is, this is going to be this infinite string of all zeros and ones, right? And maybe in that setting, an omega, which is an element of the sample space, right, it would then look like this. It would be a string that would just keep going forever and ever. So on and so forth, right? So it just keeps going, where each omega I is an element of 0 and 1, right? So a binary string, and you know, maybe 1, right, wi means that the ith marble, right, and maybe we assign them some order of appearance, right? The ith marble is, you know, white or is black, right, and so on and so forth. And so you can try to play around with this, and also you know, see if you can show why in this setting wk would be a random variable. I mean, let me just quickly kind of sketch out, maybe this is illustrative, right? So if I write down my w as a function of omega right here, one interesting thing that happens is that we're, you know, the dependence on k should really pop up here. So this one could be something like this. 1 through, so the question is how, you know, how much do we sum over, right? We're clearly going to sum omega I, right, over each one of these elements. So each one is going to say whether the, let's say this one is going to be 1 if marble I, right, the ith marble in the sequence is white, right? And so in the end we'll collect all of the all the white ones, but you know, here in this in the limit of the sum, we have to be a little bit careful, right? We have k steps, right, and it's not clear how many marbles we're summing over, right? So this I here is going to denote a particular marble. So marble 1, 2, 3, they all have some identity. So it seems like up here we would put let's see, b plus w plus k, maybe, right? What is this essentially? I'm summing up over all marbles, and this looks like the number of marbles after step k, right? And this is the identity of each one of the marbles. So maybe something like this. But I guess the main point I'm kind of getting towards is that one main distinction between this problem and the previous ones is that the number of marbles is growing, and maybe this could motivate a definition of a new variable for us that could help us determine the transition probability as well. And so how about I let nk be the total number of marbles in the box after step k. And so this would then be exactly what I wrote down a second ago. It would be w plus b, this is essentially n0, plus k, because every single pick had me sort of put one back plus an additional one, right? So this is showing that the total number of marbles in the box is growing, right? So this is total number in box by step k. And so we can try to see if we can skip to getting the transitions, right? And so let's think about this. So x always for me represents the current state of my process. And my process is this wk, right? So, you know, the kind of thinking you want to have is, if wk, which is the number of white marbles at step k, is equal to x, what are my possibilities for the number of white marbles on the next step, which is what that arrow indicates. And so it seems to me that, well, you can either not gain any, which means that you picked the other color, the black color, and alternatively you could have increased by 1, right, which is what, that was the example we ran a second ago where I picked this one and then added one more. And so the transitions here look very similar to other examples, namely they either stay the same or they go up by 1, and all we have to now do is try to specify the probabilities with which all of this happens, right? And here you kind of again want to carefully think through the events that you're considering. So what is the probability that we had some X number of white marbles, and what's the probability that, or what's the event during which that number stays the same on the next step? Well, it corresponds to the event of me picking the black, one of the black marbles. So what is that, right? Same thing with the other one. You want to list the event, right? So what happens? How could I have transitioned from X white marbles? How could I have gone to up to add 1? Well, this one is actually maybe even a little bit easier, right? To go up by 1 means I picked, right, that color. I picked the white marble, right? And so this one kind of clearly stands out as X over NK. So this is interesting, right? We see time dependence here in the transition probabilities. And the other one is, of course, by default becomes 1 minus that, right? But again, to think it through, how could we have started with X white marbles, and on the next step again had X white marbles? Well, it means we picked a black one. How many black ones are there? Well, it's NK minus X divided by NK. So we have now these transition probabilities that look different from the previous two examples in kind of two ways. One is you see this dependence on K, and the other thing that you see is that they're kind of flipped. They used to be, right, this one kind of used to be over here, and that one used to be kind of over there. That's what we had in the coupon collector problem, right, and which was essentially earn problem number 1 and number 2, and this one seems to have these transitions flipped in terms of the probabilities, and it adds this time index here. And so this is kind of a first example of a time inhomogeneous Markov chain, right? So to write this out, let's see, I'm going to erase this. So, right, time homogeneous chains do not depend, right, have transition probabilities that are time independent. In here, let's write down specifically what we've arrived at. We have that the probability of WK plus 1 is equal to Y, given the entire past history. Right, so we're now going to ask whether this is a Markov chain. And one way of doing this is to start with this expression and infer from this little transition sketch, right, what these are and whether they depend on the entire path. Clearly they depend only on this value, right, which is visible from here. We have a starting state, and we were able to determine the transitions from the starting state alone. And so clearly this is not at play, right? The entire history of the process is not at play. So this chain is clearly Markov. This process is a Markov chain, in other words. And if I close the bracket here, I will have two possible outcomes, right? One is where Y is WK, meaning that we stay the same. That's this transition. And we have Y equals WK plus 1. That's this transition. And this probability is WK over NK. And this one is NK minus WK divided by NK. And so the key kind of difference here is that this K appears in the transitions themselves, and this makes it a time inhomogeneous Markov chain. So that's our first observation. I'll throw in a little bit of an extra maybe small quiz question, just something for you to think about. Let's say that I set a new process that's equal to the following tuple, wk and nk, or maybe even just k. Right? Try to see if you can kind of pause the video and think through whether this process, this T, is a Markov chain, number one, and then ask yourself whether it's still inhomogeneous or is it a homogeneous Markov chain. So the question, the quiz question, sort of like, is TK, which is a process, so it's a bunch of these random variables, a homogeneous Markov chain. So think through that, try to put together kind of a little bit of a justification or a proof. I'll tell you that the answer is actually yes. And this type of construction is in fact called what's called a space-time chain, right? So you're always adding, you can add k as the second coordinate, and then at that point there's no longer reliance on physical time. Sort of, you know, the idea is that you're keeping track of time as another variable, and so time becomes not needed for the, you know, or at least that you can rely on the state of the process to infer time. And so this is kind of a cheap trick to take something that's an inhomogeneous chain and turn it into a homogeneous one. So now let's, you know, with that little bit of a detour, let's come back to the problem that we really want to study. And by the way, just so you know, the reason I bring this up is that you'll see that in a lot of books, the, you know, pretty much all examples and all the tools that you see that are discussed are for homogeneous chains only. And you kind of, you know, think to yourself, well, why is that? Well, that's exactly why. This space-time chain that I just constructed, where you take the original chain and put a time coordinate next to it, essentially converts any time inhomogeneous chain to a homogeneous one. So, you know, back to the goal, right? This first step, transition analysis. Once again, you start out with an expectation, right? And at this point, you can kind of, this third example we have, the third example, you can move quite a bit faster. Maybe we'll start with +1 like before. Condition on WK. Right? Then take that's step 1 of the first step transition analysis. Step 2, tower property or conditional expectation here. Then you take apart this conditional expectation, right? What are the possibilities? The possible outcomes are this one, and these are the probabilities. So let's write it out. WK +1, that's this outcome with this probability. So you have WK over N plus WK is this outcome with this probability. NK minus WK over NK. All right, almost there. Let's see, something's going to cancel. Quadratic cancels out. So I think you'll have WK, that's this one, over, I missed an NK here, over an NK. That's going to be this term. That cancels with this, and what's left is plus WK. And so now I go back up here and erase this part. And what I have is WK times 1 plus 1 over NK. So now step 3 is just to set this thing equal to, this guy equal to mu k plus 1 right? That's going to equal this expectation here. And step 3 would be to write the recurrence relation, right? And plugging this into here, you'll see that it's this, right? And this one's easy to unroll, so, you know, we could even sort of write one step of it. Minus 2, and so on and so on and so forth, right? So this one unrolls pretty easily to be, we'll have to have a W0. W0 is little w, so that's going to be the initial condition, and then a product that looks like maybe something like this. So potentially it's something like this, right? So when we get to 0, this 2 will give me, yeah, this looks right. The only question is whether this could be k minus 1. No, you'll need to pick up a k, so that looks good. Yeah. So you have this product here, and you can start, you know, seeing the kind of the main difference is that as k becomes larger and larger, you're taking a product of something that's bigger than 1. And so clearly this is increasing, right? The number of white marbles is increasing over time, which is sort of what we expected. But one question you could now ask is, what if, you know, clearly this NL here, right? What's NL? NL is equal to W plus V plus L, right? So this is a cursive L that I'm using here just because I ran out of notation, ran out of variable names, right? So this is L and this is K, this is NL. NL is the number of marbles total at step L, and so it's proportional to L. And so you can kind of ask yourself whether, well, you know, for large L or for large K, this maybe goes away, this converges to 1. Is it possible that eventually the number of white marbles just kind of becomes constant and stops growing, and the number of black ones keeps growing forever without bound, right? So you could try to see if that's true. Turns out to not be true, so that has to do with the fact that I'll give you a little bit of a hint. You could try to see if you could write this as exponential, right? You could try to write this as W times exponential sum log